So let's take a look at problem number 28 in the textbook, Survey and Fawn. So here's a little diagram, and it's always a good idea to draw diagrams so you can visualize what's happening. So we have the lead car moving at 25 meters per second. At the same moment, the chasing car, the one behind, is moving at 30 meters per second. It's trying to catch up to the lead car. And there's 40 meters separating the two. This is the before picture. Okay, so they both apply the brakes at the exact same moments, and the lead car is going to stop. And the chasing car, we want it to stop also, but just barely avoids hitting the lead car. And that's what's really, really important. We want to make sure it doesn't hit the lead car. And you should have no problem with letter A, figuring out how much time it takes the lead car to slow down and stop, right? Just an easy application of A equals VF minus V naught over time, rearranged for time. Here's the key, though. We want to make sure both the lead and chasing car pretty much arrive at the same point. Not necessarily at the same time, but they arrive at the same point. Like maybe there's a red light there, right? And so they both have to travel the distance to get to that stopping point. Which means, what do you really have to find first? Well, you have to figure out how far does the lead car move in the time it takes it to slow down. So you want to find delta x lead. Now here's the key. The chasing car is 40 meters behind the lead car to begin with. So the chasing car doesn't travel the same distance. The chasing car has extra distance to travel, right? And that's where I think some students are having trouble. You should have no problem finding that delta x lead is 156 meters. Then I'll leave it to you to figure out how far the chasing car has to move before it slows down and just barely avoids hitting the lead car. Now, the other issue some students may have is they may be confused about the time. Just because the lead car takes 12.5 seconds to stop doesn't mean the chasing car stops in the same amount of time. In fact, you can prove to yourself that it doesn't. It's asking for the minimum acceleration, just barely avoid hitting the leading car, right? Any large acceleration should be fine, but that all we need is the minimum acceleration, so it just barely travels the same amount of distance without hitting the car in front, which means that when the car in front has already stopped, the car behind, the chasing car, is still moving. It's going to be traveling for a different amount of time, which is fine, because remember, it had the extra 40 meters to travel to get there.